Hi, Nitty.
Hi, Nitty. Hope you're having a good day here. We sure are. Wow, we're doing 14.6. We're going to be, look at that learning target. I can write equations of tangent lines. Wow, how about that? We've done that before, but let's investigate this in a slightly different context. 14.6, hey, we've got day number 3. Let's say we've got a function of x, y, and z, and we find its gradient vector. And, that's something we've been dealing with, repeatedly. So we've got this gradient vector function. The partial derivatives are evaluated at a point. Once we have that, we could write the equation of a tangent plane. This is review. This is actually what we did last week. And in fact, this is something that we were dealing with. We've been writing equations of planes for quite some time. But on Friday, we also talked about writing the equations of normal lines. And what we saw is that normal vector, the vector that's perpendicular to the plane, is actually the gradient vector. That's what we really saw last Friday. And we saw that that's actually a direction vector for the normal line. So, that direction vector has the gradient components multiplied times t. So that's all review. And again, what are we seeing? Each partial derivative for both the tangent plane and the normal line are evaluated at that point in question. So we can use the ideas above to find the equation of a tangent line for functions involving only x and y. My goodness. We're going back in time. Let's go back to the good old days last year. Oh, wow. Oh, the fun that we had. Let's see. We've got this x squared all over 4 plus y squared equals 2. And last year you dealt with this problem as all calculus students do. You'd say, let's write the equation of a tangent line at a point negative 2 comma 1. Think, okay, well, we'd have to take our derivatives, and we'll take our derivative of y implicitly. What's the derivative of x squared over 4? What did that become? X over 2. 2x over 4, it's just x over 2. How about this thing? Ooh, be careful. What do we get? 2y. Yeah, dy dx or y prime. You could write it either way, right? You guys are good. You remember that. So we've got that's equal to 0, and then we have 2y, y prime would equal, negative x all over 2. And, then what? How about we multiply both sides by a half? And you could say, well, my gosh, it's y prime is equal to negative x all over 4. And then how about we multiply both sides by 1 over y? And without too much ado, we've got negative x all over 4y. But then, of course, we'd say, now, wait a minute, plug in your point to get your tangent line slope. And when we do that, we're going to plug in a negative 2 for our x, and we're going to plug in a 1 for our y value. So that's 2 over 4. That really just becomes 1/2. We okay with that? Now, what you learned was, of course, the equation of any tangent line was going to be in point-slope form. You could say, well, wow, I've got negative 2 comma 1. And you could very quickly say, well, I already know what my slope is. It's right here. And x minus negative 2, you'd get x plus 2. And you'd say, hey, look at that. We are good to go. Okay? But you might wonder why we're even looking at this problem right here. The reason is, here's the funny thing. Over and over and over and over again, what we've been dealing with this unit, this chapter, is we've been writing a lot of tangent planes. And that's fine. We could definitely do that. But hey, if we just have an equation with x and y, you could say, well, z isn't even really in the mix, so to speak. Hey, wait a minute, could we still write that out And imagine that that f of z times z minus z naught was gone. You bet. Let's write that out that way. Let's write our tangent plane equation losing the three-dimensional aspect of it. Huh. Interesting. Well, you get the idea. We could say, here's your f function of x, y, and z. And by the way, you could just as well envision that your f function could be, this whole thing minus 2. Honestly, you could go either way. You're going to get the same partial derivatives. What's f sub x? What would you get? 2x over 4 or x all over 2. What's f sub y? Well, help me out. 2y. Look at that. And then you could say, well, let's see, I'm going to have to plug in my point in question, negative 2 comma 1 for both of these. And let's see, that's negative 2 over 2. That's just negative 1. Over here, that's negative 2 times 1. Hey, that's negative 2. And again, I think I just want to go to the top of the screen here to remind you that it's f of sub x times x minus x naught plus f sub y times y minus y naught. Yeah. Was it positive 2? Oh, yes. Oh, my goodness. Good thing you're here. Thanks so much, Richa. Wow. Yeah, we would have been a little baffled why our answers were not the same. Thank you so much. If we're losing our z component, right now we could say, well, hey, let's plug that in. Here's negative 1 times x minus, well, what's your x naught? It's negative 2 comma 1. That's minus a negative 2. And how about your f sub y? Well, that's your 2 times a y minus a 1. You'd say, well, there it is. Look at that thing. This is negative 1 times x plus 2. Guys, this right here is another way to write the equation of your tangent line. Wow. You might think, are you sure about that? Well, how about we bring this thing over? Look at that. Now it becomes a positive 1. How about we divide by a 2? Wow. Look at that. Kind of cool. You lost that tangent line dimension, or the tangent plane dimension of the z. It's dropped down to just a conventional tangent line that you did last year. So if you went back to last year, you could use multi to write equations of tangent lines. Wow. Well, let's see how we're doing here as we take a look at this next part. Say we've got two functions, f and g, and they cross at a point. We have a point that's on the intersection of f and g. You might say, how can we write the parametric equations of the line tangent to the intersection of the point? Well, as you saw before, the gradient, guys, was the vector that would be perpendicular to a tangent plane. And we're going to come to this in just a moment. Let's see here. To write the equation of a line in space, and by the way, so very often we would do that, right? We'd say x is parametrically, we could write it like this. What do you need? To be able to write the equation of a line in space, you need a point. Well, that's your x naught, y naught, z naught. They will give you a point. They're going to say, here's a point of intersection, right? What else do you need? A direction vector. And that direction vector would be ABC in this regard. So the big question is, if they tell you that you have a point of intersection, really all you need to do is come up with a direction vector Any thoughts as to how that might take place? What do you think? Something about the gradients. What do you think? Gradient of f, cross product with the gradient of g. Do the cross product, and then you're going to be able to get that line. And by the way, if you look back on an old picture that I handed out to you, do you remember how when we said when the planes, two planes intersect, their normal vectors would have a cross product that lies on the line? I can bring that picture back up. Sadly, not in the video. Our video, we're running out of some time here. But let's see what we've got going on. So it says the following two surfaces meet in a curve, and we'd like to find the parametric equations for the line tangent at a given point. Let's go ahead and find the gradient vectors. Let's do f sub x. What's the derivative of f with respect to x? What do we get? 2x. How about f sub y? What do we get? 2y. And then how about with z? We get, 0, right? So the gradient of f is going to be 2x, 2y, and then 0. But I'm going to plug in the point 1, 1, 3. And I hope you could see pretty quickly that you'll get 2, 2, 0. Okay? Then I'm going to do the same thing with g. We'll say g sub x. I guess that's 1. How about g sub y? 0. And how about g sub z? That's 1. This is kind of nice because you know what? Regardless of what you're trying to plug in here for those points, the point 1, 1, 3, letting x equal 1, y equal 1, and z equal 3, it's not even going to affect these vector components. So, tell you what, this is where, and my apologies that I do not have my TI-89 out right now. And that would take me a while to do this. But I trust that you guys can get a cross product together. Okay, so we took a little pause, worked out the cross product totally with the TI-89. 2 comma negative 2 comma negative 2. Guys, this is your direction vector. This is your direction vector. So what are we seeing? That's like your A, B, C in regard to writing out the parametric equations. Look at that. Y equals Y naught plus BT, and Z equals Z naught plus CT. So what are we getting? Well, your X naught, Y naught, Z naught is the point 1, 1, 3. So you should get x equals 1 plus 2t, y equals 1 minus 2t, z equals 3, that's your z naught right here, minus 2t. This is a great, correct answer. I do want to let you know that it's possible that as you check the back of the book, you could get this answer instead. You can see that the direction vector has just been reduced. You had a 2, negative 2, comma, negative 2. And as you've got that all in here, if you can simplify a direction vector, you certainly may. And it would make life a lot simpler. Both answers are correct. And that is actually the end of 14.6. We're going to have a worksheet for our assignment.